Hello everyone, welcome to my YouTube channel which is named as Thermal Engineering by MANOJ SHENDRE. In the today's video lecture, we will see how to derive the equation for the maximum blade efficiency of a PELTON wind turbine. Okay, so these videos are exclusively made for the students who are studying in mechanical engineering with semester under Vishweshwaraya Technological University, Belgavi, right? So don't forget to like, share, and subscribe my channel. So let's start the today's video. So in the today's video, as I said, we are going to derive the equation for the condition for maximum blade efficiency of a Pelton wind turbine. Okay. So first we'll begin with how to draw a single blade, a cross-sectional view of a single blade of a Pelton wind turbine, and how to draw the inlet and outlet velocity triangles of a Pelton wind turbine. Okay. Right. So this is the cross section of a single blade of a Pelton wind turbine. This is the cross section of a single blade. Now, this is the nozzle, horizontal nozzle, and this is the direction of a jet. This is the direction of a jet. As we know that the nozzle is horizontal. The nozzle is horizontal, so that's why the inlet velocity triangle collapses to a straight line. This is a very important point in derivation that you need to keep in mind. Okay, so I'll repeat it once again. As a nozzle is horizontal, so therefore the inlet velocity triangle collapses to a straight line. Okay, so this complete vector is v1, the absolute velocity v1, which is equals to vu1. Remember, the absolute velocity has three components, namely the tangential velocity component, which is represented by vu. Second one is relative velocity component, that is vr, and third one is the axial velocity component vf. Okay. Now, this is the tangential velocity of the blade, which is represented by capital U, the tangential velocity, capital U, and the next one is the relative velocity component VR, the relative velocity component VR1, VR1. So here, the vertical component of inlet velocity triangle is equals to 0, that is VF equals to 0, because the inlet velocity triangle collapses to a straight line. Since the nozzle is horizontal, so alpha 1, the angle made by nozzle is equals to 0. So that's why we have drawn the horizontal line for inlet velocity triangle. Right. Now this is after hitting the jet, it follows the curved path, and this is the outlet. This is the outlet of the jet. This is VR2, the relative velocity component at the outlet. This is V2, the absolute velocity at the outlet, and this is VF2, that is flow velocity component at the outlet. Flow velocity component at the outlet. Okay. Now remember, the angle made by V2 is alpha 2. So alpha is the angle. Alpha is the angle for absolute velocity, right? But here V1 is horizontal, so therefore naturally alpha 1 will be equals to 0, right? Similarly, beta 2 is the angle for VR2. Beta 2 is the angle for VR2. Similarly, so here U is the tangential velocity of the blade. U is tangential velocity of the blade, and VU2 is the tangential velocity component. VU2 is the tangential velocity component. Okay, so this is the complete inlet and outlet velocity triangle for the Pelton wind turbine. So this is the beta 2. This is the beta 2, and this will be beta 2. Okay, so 180 minus beta 2. 180 degree minus beta 2. 180 degree minus beta 2. Okay, so this is the inlet and outlet velocity triangles, right? So you need to remember certain points related to the Pelton wheel turbine while deriving the equation. The first one is U1 equals to U2. U1 equals to U2, right? So here the inlet velocity or the runner at the inlet, the runner velocity U1 will be equals to the runner velocity at the outlet. The U stands for the tangential velocity of the runner, that is pi d n by 60. Pi d n by 60 here, right? Okay. Similarly, so here VR1 can also be written as VR1 can be written as the total velocity V1 minus U. V1 minus U. Okay, V1 minus U. So VR1 can also be written as V1 minus U here, right? Okay. Now from outlet velocity triangle, here you can write from the outlet velocity triangle, from the outlet velocity triangle, I can write VU2 equals to, this complete velocity component minus U. This complete velocity component minus U. This complete velocity component can also be written as VR2 cos beta 2, because we know that cos beta 2 in this right angle triangle, cos beta 2 is nothing but the total base divided by hypotenuse. Total base divided by hypotenuse. So I can write, see here, cos beta 2 can be written as the total base divided by hypotenuse. Okay, so that is U plus VU2 divided by VR2. Can I write so? Yes. So therefore, VU2 can also be written as VR2 cos beta 2 minus U. So VR2 cos beta 2 minus U here. VR2 cos beta 2 minus U. Okay. So this is from the outlet velocity triangle. Right? Okay. Now, this equation can also be written as VU2 equals to VR. Now, in place of VR2, I can write VR1. So if we ignore all the frictional losses, if there is no frictional loss, then there is no change in relative velocity component. So relative velocity component at the inlet VR1 will be equals to VR2. Okay. So here I can write VR1 equals to VR2, that is VR1 cos beta 2 minus U as it is. Okay. Now VR1 can also be written as I said here, VR1 is equals to V1 minus U. So V2 equals to VR1 is V1 minus U into cos beta 2 minus U into cos beta 2 minus U. So okay. So V1 is equals to VU2. So that is same. Now therefore, work done, you can write here. Here you can write work done per kg of water. Work done per kg of water. Work done per kg of water. In model number 2, we have seen the work done equation, that is Euler's turbine equation. So with the help of that equation, I can write work done per kg of water. Work done per kg of water. It can be written as U into VU1 plus or minus VU2 divided by GC. Now here, when we have to take the positive sign, remember, when VU1 and VU2, if both are in opposite direction, then we supposed to take here positive sign in this equation. This is a very important point that you need to remember. Similarly, if both are in same direction, VU1 and VU2 are in same direction, then we're supposed to take the minus sign here, right? Okay, a little consideration shows that the direction of VU1 is towards right. The direction of VU1 is towards right, and the direction of VU2 is towards left here, towards left, because the VU2 is horizontal component of V2. I repeat, the VU2 is horizontal component of V2. So if we take the horizontal direction here, if we take in this horizontal direction, then the direction of V2 will be towards, the direction of VU2 will be towards left. So this is towards right and this is towards left. So obviously we have to take the positive sign, right? So you can write down here as the direction of, as the directions of VU1 and VU2 are opposite, So the above equation can be written as work done per kg of water. Work done per kg of water. It can be written as U by GC into VU1 plus VU. VU1 plus VU2 here, right? VU1 plus VU. Okay. Now VU1 as it is, work done per kg of steam, U by GC into VU1 as it is, VU1 as it is, okay, plus VU2. So in place of VU2, I can write this equation. Already we got VU2 equation, that is V1 minus U cos beta 2 minus U. So let me write that equation, right? So V1 minus U cos beta 2 minus U. Cos beta 2 minus U, right? Cos beta 2 minus U. Fine. So next one, in this VU1 equals to V1, VU1 equals to V1 here, right? So let me write directly here only. See, no confusion. So already we have VU1 here, but from the inlet velocity triangle, I mean, from the inlet velocity diagram, it can say, not triangle, velocity diagram, inlet velocity diagram. So VU1 equals to V1. So V1 minus U here and V1 minus U here. Let me take outside the bracket, right? So U as it is, U by GC as it is. Now V1 minus U and V1 minus U, let me take outside the bracket, V1 minus U. And inside the bracket, we are left with 1 plus cos beta 2. 1 plus cos beta 2 here. Okay. I hope this is clear up till here, right? This is clear up till here. Okay. Now, if we consider the frictional losses or the blade coefficient, I mean the frictional losses. So while moving, while flowing the water through the blade, over the blade, so there is a friction loss between the flowing water and the inner surface of the blade. So that is called blade coefficient. That is called the blade coefficient. Okay. So that is given by CB equals to VR2 by VR1. VR2 by VR1. So I can write in this equation, I can write U by GC into V1 minus U into 1 plus CB into cos beta 2. CB into cos beta 2. Okay? CB into cos beta 2, right? Okay. Up till here, this is clear, I hope. Right? Okay, I'll continue this equation here. Okay, the derivation here. This is a continuation. Now, this is the work done per kg of water, and if we want to calculate the equation, if you want to derive the equation for maximum blade efficiency, we should get both the outlet energy and the inlet energy supplied. Okay, the work which is obtained at the outlet, which is given by this equation, this is the work done per kg of the runner, word done per kg of water. Sorry, word done per kg of water. This is the outlet. This is the outlet part, right? Now, what is the energy which is supplied to the runner? So, with the velocity v1, the jet will hits the blade. Jet will hits the blade. So that definitely it carries the kinetic energy. Definitely, it carries the kinetic energy. The jet of water will carry the kinetic energy. So that is the inlet energy. That is the inlet. Now, how to write the kinetic energy of the jet of water? That we'll see here. Okay. The energy, write down. The energy supplied per kg of water, per kg of water, per kg of water in the form of kinetic energy, in the form of kinetic energy, in the form of kinetic energy. So that is given by, so we are considering per unit mass. So half into v1 square, half into v1 square. Generally we write the kinetic energy half mv square. So if we consider the kinetic energy per unit mass, then we have to take 1 by 2, that is v1 square, and of course by gc. Gc is some constant. Gc is some constant because already we have written here also gc. Gc will get cancelled ultimately in the final equation. So therefore, the blade efficiency. Therefore, the blade efficiency is given by work done per kg of water. Work done per kg of water divided by kinetic energy. Kinetic energy supplied per kg of water. Per kg of water. Okay. So this is the outlet energy. U into V1 minus U into 1 plus cos beta 2. Let me rub this. 1 plus cos CB into cos beta 2, CB cos beta 2, and of course divided by GC here. Rub this. CB into cos beta 2, of course divided by GC here, divided by the kinetic energy supplied, this equation. V1 square divided by 2 GC. So GC will get cancelled. GC will get cancelled, right? Okay. Now upon simplification, we can write this equation as the blade efficiency is equals to 2U by V1 square. 2U, this will goes to numerator, 2U by V1 square into V1 minus U into 1 plus CB cos beta 2. 1 plus CB into cos beta 2 here, right? 1 plus CB into cos beta 2. Okay. Now here, for maximum blade efficiency, for maximum blade efficiency, this should be equals to 0. The differentiation of neta b with respect to d phi is equals to 0. Now what is phi? What is phi? Phi is nothing but speed ratio. Which is the ratio of u by v. U is the speed of the blade or runner blade, the tangential velocity of the runner, divided by v1 is the absolute velocity of the jet of water. So this ratio is nothing but speed ratio, right? Now let us write this equation in the form of speed ratio, that is phi, right? So neta b equals to, so let us split into 2 here. This is V1 square. So I'll keep V1 one term outside the bracket and will send one V1 to the denominator here inside the bracket. Okay. So I can write here 2 into 5, 2 into 5 into here. One V1 will get cancelled. V1 square, one V1 will get cancelled. 1 minus, so U by V1 is 5. U by V1 is 5 here. U by V1 is 5. Okay, U by V1 is 5. Into 1 plus CB into cos beta 2 as it is. 1 plus CB into cos beta 2 as it is. So here 2 as it is. Okay. Now a little consideration shows that this term won't be equals to 0. This term won't be equals to 0. So let us differentiate this equation with respect to 5. Let us differentiate this equation with respect to 5. Before that, let us open the bracket by multiplying here 2 5 minus 2 5 square. 2 5 minus 2 5 square into 1 plus CB into cos beta 2 as it is. CB into cos beta 2 as it is. So upon differentiating this equation, okay, because the condition for maximum blade efficiency is d neta b divided by differentiation of 5 should be equals to 0, right? So upon differentiation, 2 5 differentiation is only 2 minus 2 5 square differentiation is 4 5 equals to, and this term won't be equals to 0. This term won't be equals to 0. So let me take this term as equals to 0. Hope this is clear. I hope this is clear, right? Okay. Now I can write 5 is equals to 1 by 2. 5 is equals to 1 by 2, or 5 can also written as u equals to 5 is nothing but u by v1. Okay. So v1 will go to that side, v1 divided by 2. Okay. So this is the condition for maximum blade efficiency. This is a condition for maximum blade efficiency. So how to conclude this derivation, or what is the conclusion of this derivation, is that to obtain the maximum blade efficiency, the runner speed or the tangential velocity of the runner should be equals to half of the velocity of jet at which it hits the turbine blade. Okay. So U should be equals to half of V1. So this is a condition for maximum blade efficiency. Okay. So if we substitute in this equation, I can write. Okay. Let us substitute here the phi equals to 1 by 2 in this equation. So I can write neta B equals to suppose neta B maximum blade efficiency equals to 1 plus CB into cos beta 2. 1 plus CB into cos beta 2 divided by. So this is the required equation for maximum blade efficiency of a PELTON wheel turbine. Hope this is clear. Okay. So if you have any doubts, if you want any notes or any the previous year question papers, so kindly send your messages on WhatsApp. My WhatsApp number is 98865390074. Okay. So thank you for watching this video. Don't forget to like, share, and subscribe my channel. Thank you and have a great day.